So anyway, let's carry on with the storage and the memory hierarchy. So now I want to demonstrate this timing issue here. So let me get to my machine here. All right, and put this where it's going to show up correctly and clear. Okay, so I have this file called averagematv1.c, and I want to compile it. All right, whoa, Z, all right, C, all right, I'm going to compile it, and then let's take a look at the first 15 lines, minus N15 of that file. Oops, that's the binary. Here's the C. All right, so here's the source code of this file, and I'm just going to clear the screen to get rid of that ugly stuff. All right, so it includes, what this is going to do is define N to be 30,000, just a parameter, and then it's going to have a array. It's going to take a pointer here, and it's going to fill this array, a two-dimensional array, mat and j, ij, and it's going to fill it in a certain order. So it's just going to refer to it, going to read this array. In fact, let me just get all the source code here. Let's see how that looks. Oh, I did it again. Need the source code. All right. So down here's the main. This is going to allocate this two-dimensional array, and then start the clock, call the subroutine, and end the clock, and then print out the time it took. So the interesting action happens up here, and the point is, here it's going to index J, the second index, and then the first. So if you run this thing, it takes, I think I've got a picture here. Yeah, it took 2 seconds when I did it before. And we'll see, it looks like it's taken more than 2 seconds this time. Nope, 11 seconds. Okay, probably because I was not using an emulated Intel processor there, but a real one. Anyway, now the other one is averagematv2, and let me just do this one. I'm going to download it with a browser for the same reason I just explained, but I don't really need to use SCP for this source code. I can just copy it here and paste it into Nano. So I can Nano, okay, v2, and paste it in, and then head minus N15 2.c, and the only difference here is now I moved it to ij, and let's compare that to the first one, v1. All right, here, I and j, it doesn't seem right. This is average mat v2. It should be ji, because somehow my copy and paste did not work. How rude. Well, I'll just fix it here. I don't know what happened to go wrong there. Let's just Nano the second one, and it should be ji. Somehow it isn't. Well, I'll just fix it here. I must have had, I wonder what went wrong when I downloaded it. That's pretty disturbing. Shift refresh. There, it comes up right, ji here. Somehow before it didn't. Anyway, that should do it. And so all it does is index them in the opposite order. So if I just compile it the same way I compiled the other one, which is up here somewhere, there it is, all right. Compile version 2 the same way. All right, and then run it. The other one took 11 seconds. This one's going to take a lot longer, like 30 seconds. And that's the point here. It looks like it's doing exactly the same thing, but by indexing the same data in a different order, it takes a different amount of time, and that's what we're going to study today, how memory is used. So there's a lot of places memory goes. The registers, like EAX and EBX, are used right on the processor. Then there's a cache on the processor too, which is slower, but there. Then main memory, your RAM, is down here, and your other things like the hard disk and flash disk and SSD are much slower. So level 1 and level 2 cache are just various kinds of cache. These come built into your processor. And your storage devices, I say primary storage is registers and RAM. Secondary storage is things like the hard disk and the SSD And all right, so you can consider the capacity and the latency for these things and the transfer rate. So primary storage, you see the latency is about a nanosecond for register, 5 nanoseconds for the cache, and 100 nanoseconds for main memory. So going to memory is a process that costs a lot of time. These little registers right in the CPU, you can get to them a lot faster. The problem is there aren't very many of them, so you can't store all your data and programs in there. And there's a cache, which is intended to help, some cache right here, which is faster than the memory, which can store more information, and it's automatically assigned by the CPU. You don't explicitly control it. And then, of course, hard disk, SSD, and remote servers are much, much slower. All right, so temporal locality is one issue. So what the purpose of the cache is to store something that you've already read and you expect you're probably going to need it again soon. So instead of going back to main RAM to get it, you store it in the cache, so when you try to get it again, it will be faster. So your program tries to guess when you're going to reuse something. Now, temporal locality is just you did access this variable recently in time, so it cached it in case you'd come back to it. And spatial locality is what affects that program I just showed you, that if you've already accessed data near this in RAM, you're likely to access the other data in RAM. And this is still going, by the way, so it's going to be quite a while. Anyway, so that's the point. If I've already accessed, here I am going through a whole series of array elements in order. So I've accessed an address n and then n plus 4, and I'm likely to access n plus 8. That's a normal thing to do, to go through a whole list of objects in order. So that's temporal locality. These things are accessed repeatedly. They're in the loop. This loop keeps doing I and length and sum over and over and over. So they'd be cached because you just keep referring to them over and over. And the array elements will be cached because they're spatially near each other. All right. And so you typically load a block of data at a time, like you might load 16 bytes at a time. And if you do, that's enough for 4 integers. So you do one read to RAM to get 4 integers, and you don't need to do another read until you've processed all 4 of them. That's a way to save time. So here it was a factor of 5 between the two different versions of this program. And this one looks like it's going to be essentially forever. The first one was 11 seconds, and this is still going. So anyway, let's just try Kahoot while that runs. Let me clear this off and find the Kahoots for chapter 11. Here they are, 11A, all right. All right, so which memory has the highest cost per byte? It's going to be the registers. That's why you get so few of them. You only get 16 or 32 registers. And you get kilobytes of RAM and gigabytes of RAM and kilobytes of cache. So this is the most expensive per byte by far. What cache shares data between CPU cores? It's layer 3, and I didn't remember that. Let's take a look at the slides and go back and see. Yeah, so there. Level 1 is very close. Level 2 is slower. Level 3 goes across cores. Okay, fair enough. And so they're different speeds and such. All right. And, all right, what storage is on the CPU chip? That's the registers. The hard disk is not on the chip. And neither is the SSD. Those are very far from the CPU. All right. So, let's go back to here. And down here, okay. So then caching is the big issue. Oh, let's see if that program ever finished. It did finish, 300 seconds, and the other one was 11 seconds. So that's pretty outrageous. You know, just accessing the same data in a different order greatly increased the time. All right, so when you need data, it calculates the address of the data, and it then looks in the cache and main memory. Is that data already in the cache? If it is, then we don't need to use main memory, which, as you can see, is much slower. If it misses, then we have to go wait for main memory. And like we say, the cache might be as few as 10 cycles, the main memory might be 10 times slower. And in my case, in this machine, it was 30 times slower, but that's because I'm using an emulated processor, which complicates things. Anyway, after you have a cache miss, it's going to have to access the RAM and load it into the cache. But the problem is, of course, you keep adding memory to the cache, pretty soon the cache will be full. It's only got a few kilobytes of storage, so you have to evict some existing data. And therefore, you're probably going to have to write to RAM because the data in the cache might be different than what's in RAM, and you might have to update it. So here's 3 types of design to do this. Now, direct map is where you divide the cache into cache lines. They're each independent, and it's got the cache data block is a block of programmed data. 16 to 64 bytes typically in size, and then you have metadata, which identifies which subset of memory it holds. So you have main memory, and you just break it up into, say, 4 stripes, each, say, 32 bytes. This is hexadecimal, so that's 32. So you have 32 bytes across. You break it up into 1, 2, 3, 4, and then 1, 2, 3, 4 again, and 1, 2, 3, 4 again. And so every 1/4 of the memory is all mapped to the first cache line, and the next quarter here is mapped to that cache line, and so on. So you know exactly, if you're looking for memory, you know where it would be in the cache if it's loaded. And so to locate it, you have an index, which is going to be just a part of the address in binary, which determines where it's going to be. So it's easy to tell what part of the cache you should look in. Then the question is, does it hold a valid subset of memory? And if so, how many subsets of memory does it currently hold? That's the idea. And so you have data stored there. So you have a requested memory address. The index part here tells you which part to look in. And the tag here, the tag tells you, I think, whether you got the right one. Yeah. So what you have is, this is always going to store a block of data of a certain size, so you can skip a few bits here. That's going to be the size of it. This is the relative location in a repeating block, so that's implied by this location, and the tag is what tells you which of the many possible blocks of memory are really there. So that's how you know whether and the valid bit tells you whether this data is valid. So if it's valid, and if the tag matches that part of the address, then the information in the cache is all you need, and you don't need to go to memory. All right, so the offset is the lowest order bit. That's just offset within the block, and that identifies the cache. All right, so that's the game. All right, And so there's a read example. If you have 16-bit memory addresses, which is a really old machine, direct mapped cache with 128 cache lines and 32 cache blocks, then you'd have each block will contain 32 bytes, and there'll be a tag here and a valid bit. And so if I want to read from this address, the tag is 1010, the index is 3, and the offset is 100. So the 1010 appears here, telling me that currently this block of data has been stored in a cache. The 1 means it's valid, and the 100 offset is moving inside there. So that's how it works. You have a simple map from main memory to cache, so you can easily determine where the data should be in cache and check to see if it's really there. You want that process to be fast and efficient. And so we have a hit, the line is valid, and the tag matches, so the data should be in there. And now we offset it by the amount necessary to inside there to find it. And here's a cache miss. The index part is 001, so it would be in this line, but the tag is 1001, and I had a miss, so it was invalid prior to this access, so now I'm going to read this and write it into there. Okay. All right. And here's the miss I was thinking of, where you try to read it, and the line is valid, but the tag doesn't match. It looks to me like the tag does match. Read from this. Line is valid, but the tag doesn't match. All right. I feel like there's a mistake in this slide, or perhaps I'm missing something. Index 00011, line 3 is valid, but the tag doesn't match. Well, it sure looks to me like it matches. So I think there may be a defect in that slide, although I thought it made sense when I reviewed this months ago. Anyway, all right. So you can have a write-through cache. You modify the value in the cache and simultaneously update main memory every time you write. That's one possibility. Or you can have a write-back cache where you modify the cache but you don't update the main memory, so now you have to have an additional bit called the dirty bit. And this, of course, is going to be faster. You want to change something, you change the cache, but you don't change main memory. That way, if you change it again, you'll never have to go to main memory, and you save yourself a whole memory write, which is a slow operation. So now you're going to have a valid bit and a dirty bit recording what's going on with the cache data. So this is more complex, but it will save time. You'll do less unnecessary writes. All right, and so direct with write example. So here we have a hit. The tag matches, and the line is valid, but the dirty bit is set to 1 because I've written into it from my program, so I'll eventually have to copy that back out to main memory. All right, and that's going to be right back. So next time I want to load different data in that cache, first I have to write it into memory to save the dirty data before I can put in fresh data. All right. And all right, so cache misses are going to be, of course, cold start misses where the program has never loaded this data at all. And capacity misses are, of course, far more common, where you filled up the cache and you have to remove data because they're to make room for new data. And then there's conflict misses. If two frequently refused variables map to the same cache address, each one of these will evict the other data from the cache. And there you can get a sort of flapping. And this is a fairly common situation in computing, that you have some very inefficient condition where you keep doing and undoing some data over and over. You want to avoid this if you can. So a fully associative cache type lets any memory region access any cache location. So this is the maximum flexibility, but the highest lookup and eviction complexity. You no longer know where to look in the cache for your data. Every time you want to use it, you're going to have to search through the cache trying to find it. So this is not the general way that it's done. And set associative is the middle ground, which is what's generally done. Each memory region maps to exactly one cache set, but each set stores multiple lines. Before, it would only store one line of data, so every time we want to put new data in, we have to clear that data out. Now we're going to have a region that can store a group of lines there with the same tag. That's more flexible. I can have, say, 4 lines of data stored with the same tag here, so I will have to hunt every time through all 4 of these, looking for the one to see if it's there. So that costs me a little bit of time, but it's going to save me a whole lot of time by not having so many cache evictions. So this is the general purpose solution. All right, so when you load into it, the cache must decide which line option to use. It uses the least recently used line. That's a simple rule. Just use the one that hasn't been used recently to try to avoid conflicts. And so, again, you have the same kind of thing here. And so there'll be an example there, which I may not go through in all the detail today. But here you go. You save some data in the cache. It loads this block of data from main memory. And then when I read it, it finds it there. So it can read this data from the cache. Now when I try to read from a different address, both lines here are invalid. So the request misses. And it loads the data from main memory. And it's going to load it. All right. And here I'm going to get a miss. One line's tag doesn't match and the other is invalid. So I will update the least recently used bit to 0. So now I have 3 status bits on each one. I have a tag, which tells me what part of memory it came from. I have a dirty bit, which means data has been written to the cache that has not yet gone to main memory. I have a valid bit, which means this data is a faithful copy of what's in main memory. And I have a least recently used bit to keep track of which one is least recently used and therefore the one to be written to next time I have an overwrite in the cache. All right. And so that's the game. All right, and I think that's enough of that. So you can analyze your cache function with, say, valgrind. So if I get matrix 1 and matrix 2, I think I won't bother loading them here. You see, you can download these programs, and this one runs at 2 milliseconds, this one runs in 4 milliseconds. So if you compare them, you can use valgrind to compare them, and this one here will show you this program had 65,000 misses, but this one had 1 million misses. So one program was much less efficient at using the cache, and that's what slowed it down. And all right, and I want to take a look at these programs after all. Let's just look at the source code. We can see them right here in the browser. There. So here's the first one, matrix1.c. All right, there it is. And that's one of them. And let me just open another browser window and get matrix2.c. All right, and see if we can quickly understand the comparison between these programs. And I think it's the same thing. Oh, this is the same stuff we've seen before. I don't know why it has a new name. So it's just the difference between ij and ji, the same thing. So this one loads the data in order, a byte, byte, byte. So one load will load something like 4 integers at a time, and you only have to do that every 4 lines. This one keeps jumping ahead. If your array is 1,000 by 1,000, that's the only difference. Then it loads the first byte, then a byte 1,000 further, 1,000 further, 1,000 further. Then it goes back to number 1, 1,000 further, 1,000 further. So each fetch here requires it to read from memory, and then it loads in the cache, and the cache gets full and has to keep evicting the cache again for every single one of these additions. It has to do a cache miss and then a cache overwrite, where it has to send that data back to RAM. So this totally destroys all the value you'd get out of the cache. This uses the cache effectively, and that makes it much faster. All right. So, comments in the chat. All right, that's the game there. So, to make it more complicated, these days we have multi-core processors. So each core has its own local cache, and then there's another cache shared among the processors, which in the earlier part of this chapter, they said that would be a level 3. But anyway, I'm not going to worry about that. So 2 or more cores might have cached the same data in L1. So this one might have cached something, and this one might have cached something in the same spot in memory. Now you have a conflict. All right, so they have a cache coherence protocol to prevent this, and this will make sure that anytime a core accesses a memory location, it will check to see if any other core has updated it and updated it. So this is one of the cache coherence protocols. Modified, shared, invalid adds 3 bits to each line. M indicates it's been modified. S, it's unmodified and can be shared. I, it's invalid. So these flags will be used to prevent conflicts as the various cores try to reach the same thing. And by the way, this is the kind of thing that leads to race conditions when you have multiple cores accessing the same data. Anyway, all right, so that's the game. And so on a read, if you read the cache block, then it satisfies the read. if the cache block is in the invalid state, then it's out of date, and so it's going to have to go hunt for where the modified data is, like it might be in another core. So that's the point. All right, and I don't think I'll go through it in great detail, but you can see how that's going to keep it. You're going to keep having to read and write operations to. So the write operation is going to have to mark the invalid byte in the other ones, saying I've written to this one, I've already marked the other cache is invalid. So you're saving time because you still don't write to main memory until you have to, but you do have to write to the other caches to mark them. Don't trust this data anymore because another core has modified it. All right, and another one is snooping. A snooping controller listens for reads and writes on blocks so it knows when somebody else is writing to it, and it can mark those as invalid. That's another way to do it. All right, and so each core has its own cache, which it saves so much time that it's worth the extra burden of trying to resolve the possibly contradictory data in the different caches. And this is why caching is everywhere in computing, because the fundamental problem that you have all the time is you have something fast connected to something slow. The processor is really fast, like multiple gigahertz. It needs less than a nanosecond to do anything. All the storage devices take more time than that. So you very often have the processor waiting for something, and you try very hard to avoid that. That's what makes your computer more efficient. All right, so let's try another Kahoot. 11B. People really struggle for small increments in speed, like the persistent problem of Spectre, speculative execution violating security boundaries, has been around for years, and people are not willing to give up the speed they get from it to get security. Even a small increment in speed, like 2 or 3%, people will do crazy things to get it. I don't know why. All right, so if RAM needs to be cached, but the cache is full, what happens? That's an eviction. Now you have to remove data out of the cache to make room for the new data. All right, what does the valid bit indicate? Right, it contains data that matches the data in RAM. All right, which cache type is unfit for a general purpose CPU? Fully associative, because you have only one line of data for every line of one line of cache for every line of data, and so you have a ton of evictions. You have to keep throwing it out to make room for the next data, and that's inefficient compared to set associative.